Haloalkanes and Haloarenes. Introduction. Halogenated compounds persist in the environment due to their resistance to breakdown by soil bacteria. The replacement of hydrogen atoms in an aliphatic or aromatic hydrocarbon by halogen atoms results in the formation of alkali halide, alkyl halide, that is haloalkane, and aryl halide, that is haloarene, respectively. Haloalkanes contains halogen atoms attached to the sp3 hybridized carbon atom of an alkyl group, whereas haloarenes contain halogen atoms attached to sp2 hybridized carbon atoms of an aryl group. Many halogen-containing organic compounds occur in nature, and some of these are clinically useful. These classes of compounds find wide applications in industry as well as in day-to-day life. They are used as solvents for relatively non-polar compounds and as starting materials for the synthesis of a wide range of organic compounds. Chlorine-containing antibiotic chloramphenicol, produced by microorganisms, is very effective for the treatment of typhoid fever. Our body produces iodine-containing hormone, thyroxine, the deficiency of which causes a disease called goiter. Synthetic halogen compounds, namely chloroquine, is used for the treatment of malaria. Halothane is used as an anesthetic during surgery. Certain fully fluorinated compounds are being considered as potential blood substitutes in surgery. In this unit, you will study the important methods of preparation, physical and chemical properties, and uses of organohalogen compounds. Classification. Haloalkanes and haloarenes may be classified as follows on the basis of number of halogen atoms. This may be classified as mono, di, or polyhalogen, that is, tri, tetra, etc. compounds depending on whether they contain 1, 2, or more halogen atoms in their structures. For example, monohalo compounds may further be classified according to the hybridization of the carbon atom to which the halogen is bonded, as discussed below. Compounds containing sp3-CX bond, where X is equal to fluorine, chlorine, bromine, iodine. A. Alkyl halides or haloalkanes, that is R bond X. In alkyl halides, the halogen atom is bonded to an alkyl group R. They form a homologous series represented by Cn H2n plus 1 X. They are further classified as primary, secondary, or tertiary according to the nature of carbon to which halogen is attached. If halogen is attached to a primary carbon atom in an alkyl halide, the alkyl halide is called primary alkyl halide or 1-degree alkyl halide. Similarly, if halogen is attached to a secondary or tertiary carbon atom, the alkyl halide is called secondary alkyl halide 2-degree and tertiary 3-degree alkyl halide respectively. B. Allylic halides. These are the compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom adjacent to a carbon-carbon double bond, that is C double bond C, that is to an allylic carbon. C. Benzylic halides. These are the compounds in which the halogen atom is bonded to an sp3 hybridized carbon atom attached to an aromatic ring. Compounds containing sp2-CX bond. This class includes A. Vinylic halides. These are the compounds in which the halogen atom is bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond, that is C double bond C. B. Aryl halides. These are the compounds in which the halogen atom is directly bonded to the sp2 hybridized carbon atom of an aromatic ring. Nomenclature. Having learned the classification of halogenated compounds, let us now learn how these are named. The common names of alkyl halides are derived by naming the alkyl group followed by the name of halide. In the IUPAC system of nomenclature, alkyl halides are named as halosubstituted hydrocarbons. For monohalogen substituted derivatives of benzene, common and IUPAC names are the same. For dihalogen derivatives, the prefixes O, M, P are used in the common system, but in IUPAC system, the numerals 1, 2, 1, 3 and 1, 4 are used. The dihaloalkanes having the same type of halogen atoms are named as alkali-DAN or alkaline dihalides. The dihalo compounds having both the halogen atoms are further classified as geminal halides or gem dihalides when both the halogen atoms are present on the same carbon atom of the chain, and vicinal halides or vice dihalides when halogen atoms are present on adjacent carbon atoms. In the common name system, gem dihalides are named alkylidine halides and vice dihalides are named as alkaline dihalides. In IUPAC system, they are named as dihaloalkanes. Some common examples of halo compounds are mentioned in table. Table, common and IUPAC names of some halides. Structure, common name, IUPAC name. CH3CH2 CHCl CH3 secondary butyl chloride 2-chlorobutane. CH3 CCH2Br neopentyl bromide 1-bromo 2,2-dimethyl propane. CH3 CBr tertiary butyl bromide 2-bromo 2-methyl propane. CH2 double bond CHCl vinyl chloride chloroethane. CH2 double bond CH2Br allyl bromide 3-bromopropane. CH3Cl O-chlorotoluene 1-chloro 2-methylbenzene or 2-chlorotoluene. CH2Cl benzyl chloride chlorophenyl methane. CH2Cl2 methylene chloride dichloromethane. CHCl3 chloroform trichloromethane. CHBr3 bromoform tribromomethane. CCl4 carbon tetrachloride tetrachloromethane. CH3CH2CH2F N-propyl fluoride 1-fluoropropane. Example: draw the structures of all the 8 structural isomers that have the molecular formula C5H11Br. Name each isomer according to IUPAC system and classify them as primary, secondary or tertiary bromide. Solution: CH3CH2CH2CH2CH2Br 1-bromopentane 1 degree. CH3CH2CH2CH BrCH3 2-bromopentane 2 degree. CH3CH2CHBr CH2CH3 3-bromopentane 2 degree. CH3 twice CHCH2 CH2Br 1-bromo 3-methylbutane 1 degree. CH3 twice CHCHBr CH3 2-bromo 3-methylbutane 2 degree. CH3 twice CBrCH2 CH3 2-bromo 2-methylbutane 3 degree. CH3CH2CH CH3 CH2Br 1-bromo 2-methylbutane 1 degree. CH3 CCH2Br 1-bromo 2,2-dimethylpropane 1 degree. Example: write IUPAC names of the followings. Solution: 1. 4-bromopent 2-in 2. 3-bromo 2-methylbute 1-in 3. 4-bromo 3-methylpent 2-in 4. 1-bromo 2-methylbute 2-in 5. 1-bromobute 2-in 6. 3-bromo 2-methylpropane. Nature of CX bond. Halogen atoms are more electronegative than carbon, therefore a carbon-halogen bond of alkyl halide is polarized. The carbon atom bears a partial positive charge, whereas the halogen atom bears a partial negative charge. As we go down the group in the periodic table, the size of halogen atom increases. The fluorine atom is the smallest and the iodine atom is the largest. Consequently, the carbon-halogen bond length also increases from C bond F to C bond I. Some typical bond lengths, bond enthalpies and dipole moments are given in table. Alkyl halides are best prepared from alcohols, which is easily accessible. Table: carbon halogen, C bond X, bond lengths, bond enthalpies and dipole moments. Bond length parameter, CX bond enthalpies, kilojoule per mole, dipole moment, dBi. CH3 bond F, 139, 452, 1.847. CH3 bond Cl, 178, 351, 1.860. CH3 bond Br, 193, 293, 1.830. CH3 bond I, 214, 234, 1.636. Methods of preparation of haloalkanes from alcohols. The hydroxyl group of an alcohol is replaced by halogen on reaction with concentrated halogen acids, phosphorus halides or thionyl chloride. Thionyl chloride is preferred because in this reaction, alkyl halide is formed along with gases SO2 and HCl. The two gaseous products are escapable. Hence, the reaction gives pure alkali halides. The reactions of primary and secondary alcohols with HCl require the presence of a catalyst ZnCl2. With tertiary alcohols, the reaction is conducted by simply shaking the alcohol with concentrated HCl at room temperature. Constant boiling with HBr, that is 48%, is used for preparing alkyl bromide. Good yields of R bond I may be obtained by heating alcohols with sodium or potassium iodide in 95% orthophosphoric acid. The order of reactivity of alcohols with a given halo acid is 3 degree is greater than 2 degree is greater than 1 degree. Phosphorus tribromide and triodide are usually generated in situ, that is, produced in the reaction mixture by the reaction of red phosphorus with bromine and iodine respectively. R bond OH plus HCl in presence of ZnCl2 gives R bond Cl plus H2O. R bond OH plus NaBr plus H2SO4 gives R bond Br plus NaHSO4 plus H2O. 3R bond OH plus PX3 gives 3R bond X plus H3PO3, where X is equal to ClBr. R bond OH plus PCl5 gives R bond Cl plus PoCl3 plus HCl. ROH in the presence of red phosphorus or X2 gives R bond X, where X2 is equal to Br2I2. R bond OH plus SOCl2 gives R bond Cl plus SO2 plus HCl. The preparation of alkali chloride is carried out either by passing dry hydrogen chloride gas through a solution of alcohol or by heating a mixture of alcohol and concentrated aqueous halogen acid. The above methods are not applicable for the preparation of aryl halides because the carbon-oxygen bond in phenols has a partial double bond character and is difficult to break, being stronger than a single bond. From hydrocarbons. 1. From alkanes by free radical halogenations. Free radical chlorination or bromination of alkanes gives a complex mixture of isomeric mono and polyhaloalkanes, which is difficult to separate as pure compounds. Consequently, the yield of any single compound is low. CH3CH2CH2CH3 in the presence of Cl2 or UV light or heat gives CH3CH2CH2CH2Cl plus CH3CH2 CHClCH3. 2. From alkenes. 1. Addition of hydrogen halides. An alkene is converted to corresponding alkyl halide by reaction with hydrogen chloride, hydrogen bromide, or hydrogen iodide. Propane yields two products. However, only one predominates as per Markovnikov's rule. CH3CH double bond CH2 plus H bond I gives CH3CH2CH2I minor plus CH3CHI CH3 major. 2. Addition of halogens. In the laboratory, addition of bromine in CCl4 to an alkene resulting in discharge of reddish brown color of bromine constitutes an important method for the detection of double bond in a molecule. The addition results in the synthesis of cis dibromides, which are colorless. Example: identify all the possible monochlorostructural isomers expected to be formed on free radical monochlorination of CH3 twice CH, CH2 CH3. Solution: in the given molecule, there are 4 different types of hydrogen atoms. Replacement of these hydrogen atoms will give the following: CH3 twice CH, CH2 CH2 Cl, CH3 twice C, Cl, CH2 CH3, CH3 twice CH Cl, CH3, CH3 CH, CH2 Cl, CH2 CH3. Halogen exchange. Alkyl iodides are often prepared by the reaction of alkyl chlorides or bromides with NaI in dry acetone. This reaction is known as Finkelstein reaction. R bond X plus NaI, where X is equal to ClBr, gives R bond I plus NaX. NaCl or NaBr, thus formed, is precipitated in dry acetone. It facilitates the forward reaction according to Le-Chatelier's principle. The synthesis of alkyl fluorides is best accomplished by heating an alkyl chloride or bromide in the presence of a metallic fluoride such as AgF, Hg2F2, COF2 or SbF3. The reaction is termed as Swett's reaction. H3CBr plus AgF gives H3CF plus AgBr. Preparation of haloarenes. 1. From hydrocarbons by electrophilic substitution. Aryl chlorides and bromides can be easily prepared by electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid, catalysts like iron or iron 3 chloride. The ortho and para isomers can be easily separated due to large difference in their melting points. Reactions with iodine are reversible in nature and require the presence of an oxidizing agent, that is HNO3, HiO4, to oxidize the Hi formed during iodination. Fluorocompounds are not prepared by this method due to high reactivity of fluorine. 2. From amines by Sandmeyer's reaction. When a primary aromatic amine dissolved or suspended in cold aqueous mineral acid is treated with sodium nitrate, a diazonium salt is formed. Mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide results in the replacement of the diazonium group by Cl or Br. Replacement of the diazonium group by iodine does not require the presence of cuprous halide and is done simply by shaking the diazonium salt with potassium iodide. Example: write the products of the following reactions. Solution: 1. CHBr CH2 CH, 2. CH3CH2 CHCl CH3, 3. CH2CH2 CH2Br. Physical properties. Alkyl halides are colorless when pure. However, bromides and iodides develop color when exposed to light. Many volatile halogen compounds have sweet smell. Melting and boiling points. Methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes are gases at room temperature. Higher members are liquids or solids. As we have already learned, molecules of organic halogen compounds are generally polar. Due to greater polarity, as well as higher molecular mass as compared to the parent hydrocarbon. The intermolecular forces of attraction, that is, dipole-dipole and van der Waals, are stronger in the halogen derivatives. That is why the boiling points of chlorides, bromides, and iodides are considerably higher than those of the hydrocarbons of comparable molecular mass. The attractions get stronger as the molecules get bigger in size and have more electrons. The pattern of variation of boiling points of different halides is depicted in figure. For the same alkyl group, the boiling points of alkyl halides decrease in the order Ri is greater than Rbr, is greater than Rcl, is greater than Rf. This is because with the increase in size and mass of halogen atom, the magnitude of van der Waals forces increases. The boiling points of isomeric haloalkanes decrease with increase in branching. For example, 2-bromo-2-methyl-propane has the lowest boiling point among the three isomers. Boiling points of isomeric dihalobenzenes are very nearly the same. However, the para-isomers are high melting as compared to their ortho and meta-isomers. It is due to symmetry of para-isomers that fits in crystal lattice better as compared to ortho and meta-isomers. Density: bromo, iodo, and polychloroderivatives of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms, halogen atoms, and atomic mass of the halogen atoms. Table: density of some haloalkanes. Compounds: density gram per milliliter. NC3H7Cl 0.89, CH2Cl2 1.336, NC3H7Br 1.335, CHCl3 1.489, NC3H7I 1.747, CCl4 1.595. Solubility: the haloalkanes are very slightly soluble in water. In order to dissolve haloalkane in water, energy is required to overcome the attractions between the haloalkane molecules and break the hydrogen bonds between water molecules. Less energy is released when new attractions are set up between the haloalkane and the water molecules, as these are not as strong as the original hydrogen bonds in water. As a result, the solubility of haloalkanes in water is low. However, haloalkanes tend to dissolve in organic solvents because the new intermolecular attractions between haloalkanes and solvent molecules have much the same strength as the ones being broken in the separate haloalkane and solvent molecules. Chemical reactions. Reactions of haloalkanes. The reactions of haloalkanes may be divided into the following categories. 1. Nucleophilic substitution. 2. Elimination reaction. 3. Reaction with metals. 1. Nucleophilic substitution reactions. Nucleophiles are electron-rich species. Therefore, they attack at that part of the substrate molecule which is electron deficient. The reaction in which a nucleophile replaces already existing nucleophiles in a molecule is called nucleophilic substitution reaction. Haloalkanes are substrate in these reactions. In this type of reaction, a nucleophile reacts with haloalkane, that is, the substrate, having a partial positive charge on the carbon atom bonded to halogen. A substitution reaction takes place and halogen atom, called leaving group, departs as halide ion. Since the substitution reaction is initiated by a nucleophile, it is called nucleophilic substitution reaction. Nu minus plus C delta plus bond X delta minus gives C bond Nu plus X minus. It is one of the most useful classes of organic reactions of alkyl halides in which halogen is bonded to sp3 hybridized carbon. The products formed by the reaction of haloalkanes with some common nucleophiles are given in table. Table: nucleophilic substitution of alkyl halides, that is R bond X. Rx plus Nu minus gives Rnu plus X minus. Reagent nucleophile Nu minus, substitution product Rnu, class of main product. NaOH, KOH, HO minus, ROH, alcohol. H2O, H2O, ROH, alcohol. NaOR dash, R dash O minus, ROR dash, ether. NaI, I minus, Ri, alkyl iodide. NH3, NH3, RNH3, primary amine. R dash NH2, R dash NH2, RNH R dash, secondary amine. R dash R double dash NH, R dash R double dash NH, Rn R dash R double dash, tertiary amine. KCN, C minus triple bond N, RCN, nitrile cyanide. AgCN, Ag bond Cn, RNC, isocyanide, isonitrile. KNO2, O double bond N, bond O. R bond O bond N, double bond O, alkyl nitrite. AgNO2, Ag bond O, bond N, double bond O, R bond NO2, nitroalkane. R dash COOAg, R dash COO minus, R dash COOR, ester. LiAlH4, H, RH, hydrocarbon. R dash minus, M plus, R dash minus, R dash, alkane. Groups like cyanides and nitrates possesses two nucleophilic centers and are called ambident nucleophiles. Actually, cyanide group is a hybrid of two contributing structures and therefore can act as a nucleophile in two different ways. C standard triple bond N, C double bond, and standard, that is, linking through carbon atom resulting in alkyl cyanides and through nitrogen atom leading to isocyanides. Similarly, nitrite ion also represents an ambident nucleophile with two different points of linkage, O minus bond and double bond O. The linkage through oxygen results in alkyl nitrites, while through nitrogen atom leads to nitroalkanes. Example: haloalkanes react with KCN to form alkyl cyanides as main product, while AgCN forms isocyanides as the chief product. Explain. Solution: KCN is predominantly ionic and provides cyanide ions in solution. Although both carbon and nitrogen atoms are in a position to donate electron pairs, the attack takes place mainly through carbon atom and not through nitrogen atom, since CC bond is more stable than CN bond. However, AgCN is mainly covalent in nature and nitrogen is free to donate electron pair, forming isocyanide as the main product. Mechanism: this reaction has been found to proceed by two different mechanisms which are described below. Substitution nucleophilic biomolecular SN2. The reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows a second order kinetics. That is, the rate depends upon the concentration of both the reactants. It depicts a bimolecular nucleophilic substitution, that is SN2 reaction. The incoming nucleophile interacts with alkyl halide, causing the carbon halide bond to break and a new bond is formed between carbon and attacking nucleophile. Here it is CO bond formed between C and OH. These two processes take place simultaneously in a single step and no intermediate is formed. As the reaction progresses and the bond between the incoming nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. As this happens, the three carbon hydrogen bonds of the substrate start moving away from the attacking nucleophile. In transition state, all the three CH bonds are in the same plane and the attacking and leaving nucleophiles are partially attacked to the carbon. As the attacking nucleophile approaches closer to the carbon, CH bonds still keep on moving in the same direction till the attacking nucleophile attaches to carbon and leaving group leaves the carbon. As a result, configuration is inverted. The configuration of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind. This process is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. Configuration. Spatial arrangement of functional groups around carbon is called its configuration. See the structures A and B given below carefully. These are the two structures of the same compound. They differ in spatial arrangement of functional groups attached to carbon. Structure A is mirror image of structure B. We say configuration of carbon in structure A is mirror image of the configuration of carbon in structure B. Since this reaction requires the approach of the nucleophile to the carbon bearing the leaving group, the presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect of the simple alkali halides. Methyl halides react most rapidly in SN2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching nucleophiles. Thus, the order of reactivity followed is primary halide is greater than secondary halide is greater than tertiary halide. B. Substitution nucleophilic unimolecular, that is SN1. SN1 reactions are generally carried out in a polar protic solvents like water, alcohol, acetic acid, etc. The reaction between tertiary butyl 1 bromide and hydroxide ion yields tertiary butyl 1 alcohol and follows the first order kinetics. That is, the rate of reactions depends upon the concentration of only one reactant, which is tertiary butyl bromide. CH3,3-CBr 2-bromo-2-methyl-propane plus minus OH gives CH3,3-COH 2-methyl-propane 2-ol plus Br-. It occurs in 2 steps. In step 1, the polarized CBr bond undergoes slow cleavage to produce a carbocation and a bromide ion. The carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. Step 1 is the lowest and reversible. It involves the CBr bond breaking, for which the energy is obtained through solvation of halide ion with the proton of protic solvent. Since the rate of reaction depends upon the slowest step, the rate of reaction depends only on the concentration of alkyl halide and not on the concentration of hydroxide ion. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide and faster will be the rate of reaction. In case of alkyl halides, 3-degree alkyl halides undergo SN1 reaction very fast because of the high stability of 3-degree carbocations. We can sum up the order of reactivity of alkyl halides towards SN1 and SN2 reactions as follows. For the same reason, alkalic and benzylic halides show high reactivity towards the SN1 reaction. The carbocation thus formed gets stabilized through resonance as shown below. For a given alkyl group, the reactivity of halide Rx follows the same order in both the mechanisms. Ri is greater than Rbr, is greater than Rcl, is greater than Rf. Example: in the following pairs of halogen compounds, which would undergo SN2 reaction faster? Solution: it is primary halide and therefore undergoes SN2 reaction faster. S-iodine is a better leaving group because of its larger size. It will be released at a faster rate in the presence of incoming nucleophile. Example, predict the order of reactivity of the following compounds in SN1 and SN2 reactions. 1. The 4 isomeric bromobutanes. 2. C6H5CH2Br, C6H5CH, C6H5Br, C6H5CH3Br, C6H5CCH3, C6H5Br. Solution 1. CH3CH2CH2CH2Br is less than CH3 twice CHCH2Br is less than CH3CH2CH Br CH3 is less than CH33 CBr SN1. CH3CH2CH2CH2Br is greater than CH3 twice CH2Br is greater than CH3CH2CH Br CH3 is greater than CH33 CBr SN2. Of the two primary bromides, the carbocation intermediate derived from CH3 twice CHCH2Br is more stable than derived from CH3CH2CH2CH2Br because of greater electron donating inductive effect of CH3 twice CH group. Therefore, CH3 twice CHCH2Br is more reactive than CH3CH2CH2CH2Br in SN1 reactions. CH3CH2CHBr CH3 is a secondary bromide and CH33CBr is a tertiary bromide. Hence, the above order is followed in SN1. The reactivity in SN2 reactions follows the reverse order as the steric hindrance around the electrophilic carbon increases in that order. 2. C6H5CCH3 C6H5Br is greater than C6H5CH C6H5Br is greater than C6H5CH CH3Br is greater than C6H5CH2Br SN1. C6H5CCH3 C6H5Br is less than C6H5CH C6H5Br is less than C6H5CH CH3Br is less than C6H5CH2Br SN2. Of the two secondary bromides, the carbocation intermediate obtained from C6H5CH C6H5Br is more stable than obtained from C6H5CH CH3Br because it is stabilized by two phenyl groups due to resonance. Therefore, the former bromide is more reactive than the latter in SN1 reactions. A phenyl group is bulkier than a methyl group. Therefore, C6H5CH C6H5Br is less reactive than C6H5CH CH3Br in SN2 reactions. C. Stereochemical aspects of nucleophilic substitution reactions. In order to understand the stereochemical aspects of substitution reactions, we need to learn some basic stereochemical principles and notations, that is, optical activity, chirality, retention, inversion, racemization, etc. 1. Optical activity. Plane of plane polarized light produced by passing ordinary light through Nicol prism is rotated when it is passed through the solutions of certain compounds. Such compounds are called optically active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. If the compound rotates the plane of plane polarized light to the right, that is, clockwise direction, it is called dextrorotatory, that is, Greek for right rotating, or the D form, and is indicated by placing a positive sign before the degree of rotation. If the light is rotated towards left, that is, anti-clockwise direction, the compound is said to be levorotatory or the L form, and a negative sign is placed before the degree of rotation. Such positive and negative isomers of a compound are called optical isomers, and the phenomenon is termed as optical isomerism. 2. A molecular asymmetry, chirality, and enantiomers. The observation of Louis Pasteur, that is, 1848 that crystals of certain compounds exist in the form of mirror images laid the foundation of modern stereochemistry. He demonstrated that aqueous solutions of both types of crystals showed optical rotation equal in magnitude, that is, for solution of equal concentration, but opposite in direction. He believed that this difference in optical activity was associated with the three-dimensional agreements of atoms in the molecules, that is, configurations of two types of crystals. Dutch scientist J. van 't Hoff and French scientist C. Le Bel, in the same year, that is 1874, independently argued that the spatial arrangement of four groups, that is, valencies, around a central carbon is tetrahedral, and if all the substituents attached to that carbon are different, the mirror image of the molecule is not superimposed, that is, overlapped on the molecule. Such a carbon is called a symmetric carbon or stereocenter. The resulting molecule would lack symmetry and is referred to as a symmetric molecule. The asymmetry of the molecule, along with non-superimposability of mirror images, is responsible for the optical activity in such organic compounds. The symmetry and asymmetry are also observed in many day-to-day objects. A sphere, a cube, a cone are all identical to their mirror images and can be superimposed. However, many objects are not superimposable on their mirror images. For example, your left and right hand look similar, but if you put your left hand on your right hand by moving them in the same plane, they do not coincide. The objects which are non-superimposable on their mirror image, that is, like a pair of hands, are said to be chiral, and this property is known as chirality. Chiral molecules are optically active, while the objects which are superimposable on their mirror images are called achiral. These molecules are optically inactive. The above test of molecular chirality can be applied on organic molecules by constructing models and its mirror images, or by drawing three-dimensional structures and attempting to superimpose them in our minds. There are other aids, however, that can assist us in recognizing chiral molecules. One such aid is the presence of a single asymmetric carbon atom. Let us consider two simple molecules, propan-2-ol and butan-2-ol, and their mirror images. As you can see very clearly, propan-2-ol-A does not contain a symmetric carbon, as all the four groups attached to the tetrahedral carbon are not different. We rotate the mirror image P of the molecule by 180 degrees structure C and try to overlap the structure C with the structure A. These structures completely overlap. Thus, propan-2-ol is an achiral molecule. Butan-2-ol has four different groups attached to the tetrahedral carbon and, as expected, is chiral. Some common examples of chiral molecules such as 2-chlorobutane, 2,3-dihydroxypropanol, OCH, CHOH, CH2OH, bromochloroidomethane, BrCl, CHI, 2-bromopropanoic acid, CH3, CHBr, COOH, etc. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. A and B in figure and D and E in figure are enantiomers. Enantiomers possess identical physical properties, namely melting point, boiling point, refractive index, etc. They only differ with respect to the rotation of plane polarized light. If one of the enantiomer is dextrorotatory, the other will be levorotatory. However, the sign of optical rotation is not necessarily related to the absolute, that is, actual configuration of the molecule. A mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation due to the other isomer. Such a mixture is known as a racemic mixture or racemic modification. A racemic mixture is represented by prefixing DL or plus or minus before the name. For example, plus or minus butane to all. The process of conversion of an enantiomer into a racemic mixture is known as racemization. Example: identify chiral and achiral molecules in each of the following pair of compounds. Solution: 1, 2, 3. 3. Retention. Retention of configuration is the preservation of the spatial arrangement of bonds to an asymmetric center during a chemical reaction or transformation. In general, if during a reaction no bond to the stereocenter is broken, the product will have the same general configuration of groups around the stereocenter as that of reactant. Such a reaction is said to proceed with retention of the configuration. Consider as an example the reaction that takes place when 2-methylbutane 1-ol is heated with concentrated hydrochloric acid. It is important to note that configuration at a symmetric center in the reactant and product is same, but the sign of optical rotation has changed in the product. This is so because two different compounds with same configuration at asymmetric center may have different optical rotation. One may be dextrorotatory, that is, plus sign of optical rotation, while other may be levorotatory, that is, negative sign of optical rotation. 4. Inversion, retention, and racemization. There are three outcomes for a reaction at an asymmetric carbon atom. When a bond directly linked to an asymmetric carbon atom is broken. Consider the replacement of a group X by Y in the following reaction. If A is the only compound obtained, the process is called retention of configuration. Note that configuration has been rotated in A. If B is the only compound obtained, the process is called inversion of configuration. Configuration has been inverted in B. If a 50:50 mixture of A and B is obtained, then the process is called racemization and the product is optically inactive, as one isomer will rotate the plane polarized light in the direction opposite to another. Now let us have a fresh look at SN1 and SN2 mechanisms by taking examples of optically active alkyl halides. In case of optically active alkyl halides, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attaches itself on the side opposite to the one where the halogen atom is present. When negative 2-bromo-octane is allowed to react with sodium hydroxide, positive octane 2-ol is formed with the OH group occupying the position opposite to what bromide had occupied. Thus, SN2 reaction of optically active halides are accompanied by inversion of configuration. In case of optically active alkyl halides, SN1 reactions are accompanied by racemization. Can you think of the reason why it happens? Actually, the carbocation formed in the slow step being sp2 hybridized is planar, that is, achiral. The attack of the nucleophile may be accomplished from either side of the plane of carbocation, resulting in mixture of products. One having the same configuration, that is, the -OH attaching on the same position as halide ion, and the other having opposite configuration, that is, the -OH attaching on the side opposite to halide ion. This may be illustrated by hydrolysis of optically active 2-bromobutane, which results in the formation of plus or minus butane 2-ol. Number 2. Elimination reactions. When a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon atom. As a result, an alkene is formed as a product. Since beta hydrogen atom is involved in elimination, it is often called beta elimination. If there is possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atoms, usually one alkene is formed as the major product. These form part of a pattern first observed by Russian chemist Alexander Zaitsev, that is also pronounced as Zaitsev, who in 1875 formulated a rule which can be summarized as, in dehydrohalogenation reactions, the preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Thus, 2-bromopentane gives pent-2-ene as the major product. CH3CH2CH2 CHBr CH2CH minus OH gives CH3CH2CH double bond CH3 minus OH gives CH3CH2CH2 CH double bond CH2. Elimination versus substitution. A chemical reaction is the result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do, by and large, what is easiest for them. An alkyl halide with beta hydrogen atoms, when reacted with a base or nucleophile, has two competing routes: substitution, that is SN1 and SN2, and elimination. Which route will be taken up depends upon the nature of alkyl halide, strength, and size of base or nucleophile and reaction conditions. Thus, a bulkier nucleophile will prefer to act as a base and abstracts as a proton rather than approach a tetravalent carbon atom, that is steric reasons, and vice versa. Similarly, a primary alkyl halide will prefer a SN2 reaction. A secondary halide, SN2, or elimination depending upon the strength of base or nucleophile, and a tertiary halide, SN1, or elimination depending upon the stability of carbocation or the more substituted alkene. Reaction with metals. Most organic chlorides, bromides, and iodides react with certain metals to give compounds containing carbon-metal bonds. Such compounds are known as organometallic compounds. An important class of organometallic compounds discovered by Victor Grignard in 1900 is alkyl magnesium halide, RMGX, referred as Grignard reagents. These reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether. CH3CH2Br plus Mg dry ether gives CH3CH2MgBr, that is Grignard reagents. Victor Grignard had a strange start in academic life for a chemist. He took a maths degree. When he eventually switched to chemistry, it was not to the mathematical province of physical chemistry, but to organic chemistry. While attempting to find an efficient catalyst for the process of methylation, he noted that Zn in diethyl ether had been used for this purpose and wondered whether the Mg or ether combination might be successful. Grignard reagents were first reported in 1900 and Grignard used this work for his doctoral thesis in 1901. In 1910, Grignard obtained a professorship at the University of Nancy and in 1912 he was awarded the Nobel Prize for Chemistry, which he shared with Paul Sabatier, who had made advances in nickel catalyst hydrogenation. In the Grignard reagent, the carbon-magnesium bond is covalent but highly polar. With carbon pulling electrons from electropositive magnesium, the magnesium halogen bond is essentially ionic. Delta minus, delta plus, delta minus are MgX. Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. RMgX plus H2O gives RH plus MgOHX. It is therefore necessary to avoid even traces of moisture from a Grignard reagent. That is why reaction is carried out in dry ether. On the other hand, this could be considered as one of the methods for converting halides to hydrocarbons. Wurtz reaction. Alkyl halides reacts with sodium in dry ether to give hydrocarbons containing double the number of carbon atoms present in the halide. This reaction is known as Wurtz reaction. 2Rx plus 2Na in the presence of dry ether gives Rr plus 2NaX. Reactions of haloarenes. Number 1. Nucleophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitutions reactions due to the following reasons. 1. Resonance effect. In haloarenes, the electron pairs on halogen atom are in conjunction with pi electrons of the ring, and the following resonating structures are possible. CCl bond acquires a partial double bond character due to resonance. As a result, the bond cleavage in haloarene is difficult than haloalkane, and therefore they are less reactive towards nucleophilic substitution reaction. 2. Difference in hybridization of carbon atom in CX bond. In haloalkane, the carbon atom attached to halogen is sp3 hybridized, while in case of haloarene, the carbon atom attached to halogen is sp2 hybridized. The sp2 hybridized carbon with a greater s character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkane with less s character. Thus, CCl bond length in haloalkane is 177 parameter, while in haloarene is 169 parameter. Since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. 3. Instability of phenylation. In case of haloarenes, the phenylation formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out. 4. Because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. Replacement by hydroxyl group. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and a pressure of 300 atmospheres. The presence of an electron withdrawing group, that is NO2, at ortho and para positions increases the reactivity of haloarenes. The effect is pronounced when NO2 group is introduced at ortho and para positions. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. Mechanism of the reaction is depicted. Can you think why does NO2 group show its effect only at ortho and para positions and not at meta position? As shown, the presence of nitro group at ortho and para positions withdraws the electron density from the benzene ring and thus facilitates the attack of the nucleophile on haloarene. The carbanion thus formed is stabilized through resonance. The negative charge appeared at ortho and para positions with respect to the halogen substituent is stabilized by minus NO2 group, while in case of meta-nitrobenzene, none of the resonating structures bear the negative charge on carbon atom bearing the minus NO2 group. Therefore, the presence of nitro group at meta position does not stabilize the negative charge and no effect on reactivity is observed by the presence of minus NO2 group at meta position. Number 2. Electrophilic substitution reactions. Haloarenes undergo the usual electrophilic reactions of the benzene ring such as halogenation, nitration, sulfonation, and Friedel-Crafts reactions. Halogen atom, besides being slightly deactivating, is O-P directing. Therefore, further substitution occurs at ortho and para positions with respect to the halogen atom. The O-P directing influence of halogen atom can be easily understood if we consider the resonating structures of halobenzene as shown. Due to resonance, the electron density increases more at ortho and para positions than at meta positions. Further, the halogen atom, because of its -I effect, has some tendency to withdraw electrons from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene, and hence, the electrophilic substitution reaction in haloarenes occurs slowly and require more drastic conditions as compared to those in benzene. Number 1. Halogenation. Chlorobenzene plus Cl2 in the presence of anhydride FeCl3 gives 1,4-dichlorobenzene major plus 1,2-dichlorobenzene minor. Number 2, nitration. Number 3, sulfonation. Number 4, Friedel-Crafts reaction. Chlorobenzene plus CH3Cl in the presence of anhydride AlCl3 gives 1-chloro-2-methylbenzene minor plus 1-chloro-4-methylbenzene major. Example: although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic aromatic substitution reactions. Why? Solution: chlorine withdraws electrons through inductive effect and releases electrons through resonance. Through inductive effect, chlorine destabilizes the intermediate carbocation formed during the electrophilic substitution. Through resonance, halogen tends to stabilize the carbocation and the effect is more pronounced at ortho and para positions. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. The resonance effect tends to oppose the inductive effect for the attack at ortho and para positions and hence makes the deactivation less for ortho and para attacked. Reactivity is thus controlled by the stronger inductive effect and orientation is controlled by resonance effect. Number 3. Reaction with metals. Wurtz-Fitting reaction. A mixture of an alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether and is called Wurtz-Fitting reaction. Fitting reaction. Aryl halides also give analogous compounds when treated with sodium in dry ether, in which two aryl groups are joined together. It is called fitting reaction. Polyhalogen compounds. Carbon compounds containing more than one halogen atom are usually referred to as polyhalogen compounds. Many of these compounds are useful in industry and agriculture. Some polyhalogen compounds are described in this section. Dichloromethane, that is methylene chloride. Dichloromethane is widely used as a solvent, as a paint remover, as a propellant in aerosols, and as a process solvent in the manufacture of drugs. It is also used as a metal cleaning and finishing solvent. Methylene chloride harms the human central nervous system. Exposure to lower levels of methylene chloride in air can lead to slightly impaired hearing and vision. Higher levels of methylene chloride in air cause dizziness, nausea, tingling, and numbness in the fingers and toes. In humans, direct skin contact with methylene chloride causes intense burning and mild redness of the skin. Direct contact with the eyes can burn the cornea. Trichloromethane, that is chloroform. Chemically, chloroform is employed as a solvent for fats, alkaloids, iodine, and other substances. The major use of chloroform today is in the production of the Freon reagent R22. It was once used as a general anesthetic in surgery, but has been replaced by less toxic, safer anesthetics such as ether. As might be expected from its use as an anesthetic, inhaling chloroform vapors depresses the central nervous system. Breathing about 900 parts of chloroform per million parts of air, that is 900 parts per million, for a short time can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the liver, that is, where chloroform is metabolized to phosgene, and to the kidneys, and some people develop sores when the skin is immersed in chloroform. Chloroform is slowly oxidized by air in the presence of light to an extremely poisonous gas, carbonyl chloride, also known as phosgene. It is therefore stored in closed dark-colored bottles, completely filled so that air is kept out. 2CHCl3 plus O2 in the presence of light gives 2COCl2 phosgene plus 2HCl. Triodomethane, that is iodoform. It was used earlier as an antiseptic, but the antiseptic properties are due to the liberation of free iodine and not due to iodoform itself. Due to its objectionable smell, it has been replaced by other formulations containing iodine. Tetrachloromethane, that is, carbon tetrachloride. It is produced in large quantities for use in the manufacture of refrigerants and propellants for aerosol cans. It is also used as feedstock in the synthesis of chlorofluorocarbons and other chemicals, pharmaceutical manufacturing, and general solvent use. Until the mid-1960s, it is also widely used as a cleaning fluid, both in industry, as a degreasing agent, and in the home, as a spot remover and as fire extinguisher. There is some evidence that exposure to carbon tetrachloride causes liver cancer in humans. The most common effects are dizziness, lightheadedness, nausea, and vomiting, which can cause permanent damage to nerve cells. In several cases, these effects can lead rapidly to stupor, coma, unconsciousness, or death. Exposure to CCl4 can make the heartbeat irregular or stop. The chemical may irritate the eyes on contact. When carbon tetrachloride is released into the air, it rises to the atmosphere and depletes the ozone layer. Depletion of the ozone layer is believed to increase human exposure to ultraviolet rays, leading to increased skin cancer, eye disease, and disorders, and possible disruption of the immune system. Freons. The chlorofluorocarbon compounds of methane and ethane are collectively known as freons. They are extremely stable, unreactive, non-toxic, non-corrosive, and easily liquefiable gases. Freon 12, that is CCl2F2, is one of the most common freons in industrial use. It is manufactured from tetrachloromethane by Schwartz reaction. These are usually produced for aerosol propellants, refrigeration, and air conditioning purposes. By 1974, total freon production in the world was about 2 billion pounds annually. In stratosphere, freon is able to initiate radical chain reactions that can upset the natural ozone balance. PP-dichlorodiphenyl trichloroethane, that is DDT. DDT, the first chlorinated organic insecticides, was originally prepared in 1873, but it was not until 1939 that Paul Muller of Gigi Pharmaceuticals in Switzerland discovered the effectiveness of DDT as an insecticide. Paul Muller was awarded the Nobel Prize in Medicine and Psychology in 1948 for this discovery. The use of DDT increased enormously on a worldwide basis after World War II, primarily because of its effectiveness against the mosquito that spread malaria and lice that carry typhus. However, problems related to extensive use of DDT began to appear in the late 1940s. Many species of insects developed resistance to DDT, and it was also discovered to have a high toxicity towards fish. The chemical stability of DDT and its fat solubility compounded the problem. DDT is not metabolized very rapidly by animals. Instead, it is deposited and stored in the fatty tissues. If ingestion continues at a steady rate, DDT builds up within the animals over time. The use of DDT was banned in the United States in 1973, although it is still in use in some other parts of the world.